won the lottery, like the big lottery, like the 476 million, I think I said I'd give you 100,000, didn't I?
Yeah, you definitely.
I really appreciate that.
I would.
Yep.
Absolutely.
Yeah, you
Yep.
did.
You might not see me anymore, but you can remember me with that. How's that sound?
Yeah. Well, you probably never see me again.
I keep trying to win that thing. You know what? That sounds like a pretty good idea. Maybe we can make that work someday. I'll see if it's kind of days off she has coming up. Or maybe I'll just put her to work on a weekend and we can do a Monday. Sound good? But you've got to be a bug in my ear because this thing up here is very forgetful. All right, my friends, let's take a look at this right here. It says, given the following, this function right here, so I've got an integral from lower limit -1 to upper limit of 1 of some function in the end equals what value? Okay, I've got an integral from lower limit 1 up to 4 of some function equal to what here?
-2.
And then from -1 to +1, a different function. Notice the difference right here. It's not h of x, it's what, or it's not f of x, it's h of x, and that's equal to what? So find each of the following integrals. So we want to see if we can't use some of these rules right up here. Okay? So take a look at the first one. We're doing the integral from -1 to 4 of f of x dx. Any ideas on that one?
Well, it would just be 1. Wouldn't it just be like 5 plus -2?
How you getting 5 plus -2 there, Ellie?
Is it wrong?
Nope.
Well, because you have the 4 to 1 plus the like 1 to -1.
So you're telling me we're doing -1 to 4 totally, and you're telling me we know the -1 to 1 already, right?
Yeah.
So this, I don't know what it is. I'm just going to put the values right in here. I'm not going to draw the graph up here. But from -1 to +1, what is that?
That would be 5.
5. So we got this right here. And then if I go 1 to 4,
It's gonna be -2.
-2 down here somewhere, right?
Yeah.
So if I want the total area, you can get what value there?
3.
3. My question is, which rule are we using up there of the 5?
I use the additivity.
Additivity rule, yep. This is kind of the same one that says, hey, we've got a situation in this right here where I could say, well, to get from -1 lower limit to an upper limit of 4, what do you notice about the upper limit here and the lower limit here? Aren't they the same?
Yeah.
So couldn't I put those together to get from -1 to +4? Okay, we all understand why that's going to be 3 there?
Yeah.
Okay, how about part B? We're going from lower limit -1 to +1 of 2 times f of x plus 3 times h of x. Okay, well that's convenient because we've got 2 -1s to 1 here and here. Okay,
So would you take the functions and multiply them by?
yep, so f of x right here. What would the integral for, so I'm going to write this out, is that okay? This would be like 2 times the integral of -1 to +1 of f of x.
Oh, because you can move it out.
Yep. Plus, and we can break these up, right? So we can go sum and difference on this, and we can go plus 3 times the integral from -1 to +1 of h of x, right? Okay. Well, guys, what's the integral from -1 to +1 for f of x?
5
Well, we're going to do what to that?
times by 2, so 10
10 plus,
plus 21 because it's 7 times 3.
okay? So this integral from -1 to +1 of h of x is what value here?
20 or 7.
Yep, very good. So 10 plus 21, what's this one have to be, friends? Good. Okay. And then, like I said, I've kind of got a mess over here, so let me kind of squeeze this down a little bit.
So what rule would you call that we just used?
So that one right there would be a combination of rules.
It'd be the,
So we pulled the multiples out front for the both. So see how I pulled the 2 and the 3 out here for both of them?
yeah.
That would be this one right up here, constant multiple rule. But I also use sum and difference rule because we had really 2 different functions being added together, right?
Yeah.
I made that the sum of 2 different integrals right there. So it's kind of a combination of rules 3 and 4 there.
Okay.
Okay. All right, part C. I'll see how good we are on part C. We're doing the definite integral from 4 to 1 of f of x. Anybody have thoughts on that one?
Well, it flips.
Yep, so if you notice right here, we've got a definite integral of f of x that goes from 1 to 4, right? and that's negative 2. So what's going to happen when I flip the limits or switch the limits upper to lower and lower to upper?
It's gonna negate the final product.
Yeah, it's going to negate our answer. That would be this order of integration rule up here, right?
Mm-hmm.
So if the original was negative 2, if I switch the limits, what's negative 2 going to turn into?
2.
Positive 2 right here. Okay, very good. Kids, what questions on that? Okay. Kids, I think there's something that's going to be pretty important to you. This is going to be a reoccurring theme as we move throughout antiderivatives and integration here throughout the rest of the trimester right here. But objective 4, pretty important. Now, normally I wouldn't show you some antiderivative tricks, but I'm going to probably do that with you guys to make sure we're cool with this. Okay? Fundamental theorem of calculus. Big concept right here. Okay? It says if f is continuous at every point of the interval where lower limit is a and the upper limit is b. So guys, when you see this right here, you guys see this notation right here?
Mm-hmm.
That just says we're on a closed interval starting at a and ending at what?
B.
B, okay? It says, and if f is any antiderivative of little f, so I should read this differently, and if capital F is any antiderivative of little f on that interval from a to b, then it says the integral from lower limit a to upper limit b of your f of x function is given by the following. It is equal to f of b.
Big F?
Yep, and I'll talk about the difference here in a second, minus big F of A. Okay? So here's what they're saying with these F's right here. If I have a capital function f of x, what they're saying right here, it gets kind of confusing, and I don't know why they do this, but they do using this notation. Then if I had capital F prime of x like this, kids, they're saying that's little f of x now. Okay? So what they're kind of saying is this. If you have a function, capital F of x, its derivative is what? Little f of x. So if they start out with a function little f of x, then are we looking for a derivative to go backwards or an antiderivative? Okay, so going from little f of x back to capital F of x, we're kind of looking for an antiderivative there, okay? And that's the notation they use for this fundamental theorem of calculus. Typical, they're going to give you a lowercase letter for your function. Okay, so the antiderivative then would be the uppercase letter of that. Does that make sense? Okay.
Wait, but what is the F, the big F prime of X?
Okay, so like I was saying right here, if I had some function, capital F of x, and I took the derivative of that, that capital F prime of x is like little f of x now in this chapter. So little f of x is going to be like the derivative of, so this capital F prime of x and little f of x kind of mean the same thing right there. Okay, does that make sense?
Yeah, it just kind of looks like it's like.
Yeah, it's confusing, and until you've had some practice with it, it can be a little confusing at the beginning, but you'll get through it, okay? Let me give you an example, guys. I'm going to cheat this a little bit. So, here's the deal. As an example, we have the definite integral. What are my limits, kids?
1 and 2.
Okay. You guys want some shortcut rules for finding antiderivatives? Okay. Now, can I show you something real quickly? Desmos is a pretty sweet thing, all right? And I question showing you this here, but I'm going to show it to you anyway because I'll require some work out of you. But watch this right here. Let's jump into Desmos. I'm already there, okay? Check this out right here. In Desmos, you see this functions button right here? If you click the functions button, there's this little class called, calculus right there. You see that little calculus thingy right there? You see that little integration symbol? You can actually throw that little guy right in there. And guess what? It's going to ask you for a...
Upper limit and lower.
Exactly. What's our lower limit, kids?
3 or 1.
Is it 1? What's the upper limit?
3.
Okay, here comes the function. Was it 3x squared?
Yep.
Okay. I'm going to show you how this works. They just give you the value there, don't they? Okay, I'm gonna figure out how I get this thing to graph here in a little bit, but what do they say the value is?
26.
26. Okay, you guys cool with that?
Mhm.
Now, what if I told you you could do that without having to use decimals? Okay, let me just show you what the function 3x squared looks like. Okay, there's that graph. And what were my limits again?
1 and 3.
Okay, you guys kind of see this graph right here. There's 3x squared. If I could go into this area right here, bounded by the x-axis, you see this area that's kind of shaped like this? It's almost like a trapezoid in shape. Okay, I'll zoom out a little bit. Maybe I can see that whole thing. But you guys kind of see this little area right in here?
Yeah.
Okay, that area is 26 square units. Now, here's how fundamental theorem of calc works, okay? Guys, we're going to kind of talk about it relative to power rule, all right? Let me ask you this question. 3x squared right here, okay? 3x squared is the derivative of some function, which means if 2 is the power to end with, what power did we take the derivative with? When, you know, your power rule, your power was always coming down by how much all the time?
1.
1. Okay, so what power did this have to come from to get that derivative?
3.
Had to come from a third power, okay? Can you think of a function that you could take the derivative of to get 3x squared, where 3x squared is a derivative? In other words, can you think of the antiderivative of 3x squared?
X to the 3rd.
X to the third, because if you had x to the third here, where would that 3 move to?
To the front.
Front, 3x, and then bring that power down 1, makes 3x to the second. So the antiderivative of 3x squared would be what?
X to the 3rd.
Okay, here's a little shortcut for you. You want it? Okay, by power rule here, if you're looking to find an antiderivative, here's how this works. Okay, anytime we're looking for antiderivatives, the antiderivative can be found by saying, okay, let's take our original function, 3x squared, but we're going to add 1 to our power. So this will become 3x to the what, kids?
3rd.
Now, the antiderivative for power stuff like this is whatever your new exponent becomes, you're going to put that value in the denominator as well. So my exponent, we moved it up 1 by power to 3, but my new exponent now is what?
3.
So we put a 3 down here.
Yep. Now.
And what do the 3's do to each other?
Cancel.
So my antiderivative is x to the 3rd. Whoops, I forgot the 3 there. Antiderivative is x to the 3rd. And I put this bar behind here. Okay, I put this bar behind here, and then I put my limits up here. So this means, and it's written right down here, it says, note this simple bar means evaluated from, so above you would say, the antiderivative is x cubed evaluated from what to what?
1 to the 3rd.
Okay, let me show you this right here. Okay, so, using the fundamental theorem of calculus in here, which states the following. This function right here is kind of like your f of x. I just gave you the shortcut to finding the antiderivative, which we now define as capital F of x, which in this case was x cubed. What did we say the area of this was going to be by decimals? So what we do is we say, all right, let's take f of 3, f of the upper limit, minus f of the lower limit 1, okay? So what function are we concerning ourselves with here? What was the antiderivative we came up with?
X.
X to the 3rd. Okay, so we're going to go in here and we're going to evaluate f of 3, which would be 3 to what power?
To the 3rd.
Minus 1 to the 3rd, right? Well, my friends, what is 3 to the 3rd? 27. What is 1 to the 3rd?
Oh my gosh, it's 1.
And what's the difference of 27 and 1?
26.
Okay. So just making sure we're good with this. Here's a function. We'll see how good we are. I'm giving you little f of x. What's capital F of x in this case then? What do you you gonna do with your power first?
Add 1 plus 1.
Bump it up 1, right? So we would call this 2x to the fifth, but by rule I gotta put that over.
Over 5.
Okay, think about your derivative here, working backwards. What's 5 times 2 here? 10 divided by 5 is the 2. X, bring the power down, 4. Works, right? Okay, let's try some of these using fundamental theorem. We're not gonna use decimals on this, right?
Wait, so would you just leave it like that?
Yep, or you could call it 0.4x to the fifth,
Okay.
if you want.
Like, could you do 2 over 5x to the 5th?
Yeah.
Is that like the same?
Yep,
Okay.
same thing. All right. I'm going to test you on some of these. You ready? Integral from 1 to 3 of x dx. What would the antiderivative of x be? Or can you think of a function that you could take the derivative of that would get you to x? And some people are so quick to say, it's 1. I was like, if we were doing derivatives, yes, but we're doing antiderivatives. What's the power in x really, kids?
1
Okay, so this could become x to the
to the 2nd
over what?
over 2.
Evaluate
One
it,
half.
what and what? Right?
Yeah.
Okay, so some people say, can I call that 1/2 x squared? Absolutely you can right there. Okay, so if I call this 1/2 x squared, that's cool. All right, so help me out here, guys. If we go with this one, we're gonna go f of 3 now. Minus f of 1. Okay, plug 3 in. What's 3 squared, kids?
9.
Then half of 9 would be what? Okay, so this becomes 4.5. Okay, plug 1 in.
1 over 0.5.
What should we get?
4.
Okay. So by doing those simple rules with antiderivatives involving power functions, we can add one and get away with it. Now, if you notice up there, have I given you all power functions? So we got to think. Again, understand this. What's given here in little f of x, kind of like a derivative already. Question becomes, can you think of an original function that got us that derivative? Well, guys, if you think about 2e to the 2x, if you remember, if I had, it's got a function with e in it, right? So maybe over here, if you guys remember your derivative rules, a derivative of e to the u, you remember what the derivative was? It was u prime e to the u, okay? In which case, the 2 is kind of like the u prime, and this is e to the what?
2x.
Okay, so that 2x would be like the u, okay? So if I'm going from this back to this, what's the antiderivative going to be? If u prime was the 2, e to the 2x, then the antiderivative was just e to the u. So the antiderivative is just e to the what?
2x.
Okay? So what we're really evaluating here, guys, the antiderivative of this is e to the 2x. And this is a little trickier, but evaluated at what?
2.
Okay, so this would become e to the what first?
E to 2x.
So e to the upper limit, e to the 2 times 2 would be e to the what?
4.
Minus e to the what?
E to the second.
Yep, 2 times 1 right here would be second. Now, if you want to leave your answer like that, I'm cool with that. If you want to punch that in a calculator and see what that is for an approximation using decimals, I'm okay with that. Okay? But part of this is going to be saying, how do I work backwards to find the antiderivative? We've taken a lot of derivatives in here, right? Okay, and I'll walk you through this stuff. I'll help you out when you have questions on it, but I think you'll catch on pretty quickly how to find them, all right? How about the sine of x? Can anybody think of a function? What's the derivative of sine? Remember it?
Negative cosine.
Derivative of sine was cosine. What was the derivative of cosine? Negative sine. So how would I figure out how to get to a derivative of positive sine x? If the derivative of cosine is negative sine, then you'd have to take the derivative of negative cosine to get to what?
Sine.
Okay, so what's the antiderivative of sine x?
Negative cosine.
Evaluated where and where, friends?
Pi
Pi and what?
0.
You want me to tell you what the values are? If I go negative cosine of pi, let's see, cosine of pi. Okay, I gotta think about this. Here's my unit circle. Cosine, remember, goes left and right, right? Okay. Here's here. Pi is clear over here. So the cosine of negative pi would be -1. But since we've got a negative out in front here, so it's going to be +1. So f of pi would be +1. Minus f of 0. Well, my friends, f of 0 is clear over here on the right, but that's a +1 over there for cosine. But the negative sign really makes it a, so we go minus -1. What's that going to equal?
2.
2. Now, again, can decimals help you figure out some of these values?
Mm-hmm.
Yes, but what decimals can't help you do is figure out what? Antiderivative, can it? Okay. You can't figure out these values by fundamental theorem? No. Okay, so I'm going to be looking for this stuff. Although I do think decimals would be a great tool to help you do what? Check some answers on it, okay? I think it would be a great tool to help you check some work and check some answers, okay? Big concept. What's the name of it again? Fundamental Theorem of Calculus. Find your antiderivative and then take the difference at the upper limit and the lower limit within the antiderivative. Okay? Do y'all have what you need from this page right here, friends? Okay. Next page. Oh. I gave you some cheat sheet rules here. Okay, for antiderivatives. Okay? It says according to our fundamental theorem of calc, when we solve this using evaluation, we can solve integrals or an area under a curve, displacement, position values, distance, total quantity, etc. Algebraically, as long as we can find a what? Okay, now guys, you see that plus c that's on the end of all of them for antiderivative? That just means plus some constant c. So think of it this way. What's the derivative of 2x? 2. What's the derivative of 2x plus 6?
2.
Plus 6 is like a constant, right? So when I take an antiderivative, they're always putting plus c on here, okay? Now, you'll learn more about common antiderivatives as we move forward right here. So the part that you're kind of looking for common antiderivatives, kind of forget this plus c part for now involving fundamental theorem, okay? So for instance, I kind of talked about this one right here, x to the n power, where n's not -1. What did we do to our power right here? We added what? 1, and then this 1 over n plus 1, that's like the division of n plus 1 at the bottom. Okay, it's like add 1 to your power. What's the antiderivative of cosine?
Sine.
What's the antiderivative of sine? Oh, if I looked at this page first, we'd have known that right away, right? Okay, what's the antiderivative of e to the x? Well, it's e to the x, and so on. Okay, so this is a good little table to start with, but this isn't going to be the say-all, end-all for all antiderivatives. We got a lot more to look at as we progress this year, but it'll be a good little chart to help you with here, okay? All right, I think that's it on the notes, isn't it? Do you guys have anything beyond that? Okay, guys, this section of notes is crucial. You've got to understand it in order to move forward. So let me go ahead and stop this here. I'm going to give you a little time to start your assignment today.